Every year, millions of tons of refractory bricks are produced worldwide, a material capable of withstanding temperatures over 1,500 degrees Celsius and protecting structures where metal melts or flames erupt. Just to line one blast furnace requires up to 4,000 tons of this stone that fears no fire. But what gives it such strength? Why would metallurgical giants, cement plants, and glass furnaces grind to a halt without it? And most importantly, what technological secret turns ordinary clay into armor against flames? Watch until the end, and you'll find out what they don't write in textbooks. At the heart of it all lies not ordinary red clay, which is used for building bricks, but its special variety, refractory or kaolin clay. Its uniqueness lies in its chemical composition, where two oxides dominate, aluminum oxide and silicon dioxide. It is their high content and the correct ratio that give the raw material its main property, an extremely high melting point. To give the future product stability and predictability, manufacturers resort to a technological trick. Part of the mined clay is not sent directly into production, but is first fired in kilns at temperatures up to 1,500 degrees Celsius. As a result of this process, the clay loses its plasticity, sinters, and turns into a very strong, stone-like material called chamotte. This finished chamotte is then crushed and used as the main component, with a certain amount of fresh, plastic clay added to it, which acts as a binder. This approach solves a key problem. It significantly reduces the shrinkage of the products during final drying and firing, preventing deformations and cracking. So, the process begins with the preparation of components. The mined clay and other rocks, as well as the pre-prepared chamotte, are sent to the crushing line. Giant crusher jaws break large pieces, and then roller and ball mills relentlessly grind them into a fine powder with a clearly defined grain size. Control of the fractional composition is extremely important because the future density, and consequently, the strength and thermal conductivity of the brick depend on how tightly particles of different sizes can pack together. After crushing, automated dosing systems weigh each component, chamotte powder, clay powder, water, and other possible additives, with computer precision according to the recipe for a specific type of refractory. This entire mixture is sent to powerful mixers, where it is intensively mixed until a completely homogeneous mass, known as the batch, is formed. Next, the formless mass must acquire its shape. The most common method is semi-dry pressing. The batch, containing a minimal amount of moisture, is loaded into high-strength metal molds. Then, a press exerts an enormous force, measured in hundreds of tons on it, pressing the mass into a steel die. Thanks to this colossal pressure, the particles get as close as possible, displacing air, and at the output, we get a dense, smooth block with perfect geometry. A green brick. Although it already has its shape, it is still very fragile and not resistant to moisture. The next stage requires not strength, but patience and precision. The green bricks are carefully placed on kiln cars and sent to long tunnel dryers. This is a slow and delicate stage, which can last from 1 to several days. Inside the dryer, a carefully controlled microclimate is maintained. The temperature is gradually increased, and the humidity is reduced. It is important that the moisture leaves the brick as evenly as possible from its entire thickness. Any rush or violation of the regime will lead to the outer layers drying faster than the inner ones, which will create critical internal stresses and simply tear the brick apart with cracks from the inside. When all the physically bound water is removed, the culmination of the entire production cycle begins: firing. The brick enters the fiery tunnel of the kiln, where a true rebirth awaits it. Slowly moving through different zones of the kiln, it is gradually heated to peak temperatures, which for chamotte brick are 1,400 degrees Celsius, 100 degrees Celsius, and for high alumina types can exceed 1,750 degrees Celsius. This is not just drying, it is a deep metamorphosis. At such temperatures, complex chemical reactions are triggered, mineral particles soften on the surface and sinter together, forming a strong and dense ceramic structure. In the system of aluminum oxide and silicon dioxide, new crystalline compounds are formed, In particular, needle-like crystals of mullite, which, like reinforcement, permeate the entire structure of the brick, giving it exceptional strength and thermal stability. Having passed the peak of heating, the brick just as slowly passes through the cooling zone. This stage is no less important, as rapid cooling would cause thermal shock and destroy the product that has just gained strength. At the exit of the kiln, a completely new product appears. A hard, ringing, slightly rough to the touch block that is not afraid of fire. Next, only inspection. Each product undergoes a rigorous inspection for compliance with geometric dimensions and the absence of defects, after which it is marked, packaged, and sent to fulfill its main mission, to contain the flame. To realize the true significance of refractory bricks, it is worth looking at the language of numbers. The global market for refractory materials is an industry valued at over 30 billion euros annually, and over 70% of this entire colossal mass of products is consumed by one industry, ferrous metallurgy. Just for the internal protective lining of one large blast furnace, it can take from 2,000 to 4,000 tons of refractories, and one steel taming ladle, which transports hundreds of tons of liquid metal, eats up several sets of lining per year. A standard Chamotte brick of grade SHA5, which is the most common, weighs about 3.5 kilograms and is capable of withstanding temperatures up to 1,690 degrees Celsius. On an industrial scale, this means that millions of tons of these bricks stand guard annually, containing thermal energy equivalent to the energy of thousands of volcanoes. The field of application of refractory bricks is as wide as the hot processes that form the basis of our civilization. Its main consumer is, without a doubt, metallurgy. Here, it is absolutely indispensable. Refractory bricks are used to line the inside of blast furnaces, where pig iron is born from ore. They are used to line oxygen converters and electric arc furnaces, where pig iron is transformed into steel. Huge steel taming ladles that transport molten metal are also protected on the inside with a lining of refractories. Moreover, for each zone of the unit, its own special type of brick is selected, capable of withstanding not only temperature, but also the chemical aggression of the melt and slag. The second most important consumer is the cement industry. Long, several hundred meter long rotary kilns, in which cement clinker is fired at a temperature of 1,450 degrees Celsius, are completely lined on the inside with special types of refractory bricks. Without this protection, the steel shell of the kiln would burn through in a matter of minutes. The glass industry also cannot exist without refractories, huge tank furnaces, where the glass mass is melted at a temperature of about 1,600 degrees Celsius, are lined with special, very resistant types of bricks that can withstand not only the heat, but also the aggressive chemical effects of molten glass for years. Besides these giants, refractory bricks are used in the thermal power industry for lining boilers and furnaces, in the chemical and oil refining industries for lining reactors, and in waste incineration furnaces. And of course, on a much smaller scale, we encounter it in everyday life. It is from Chamotte brick that fireplaces, stoves, and chimneys are built, as it guarantees safety and durability, reliably containing the heat in the heart of our home. Every year, the world recycles millions of tons of wood waste, and a large part of this trash gets a second life in the form of what we see every day at home, at work, or in stores. Particle board. Imagine this: mountains of wood chips, sawdust, and old furniture being transformed into smooth panels, capable of holding weight, keeping their shape, and becoming the foundation of modern interiors. But how is a monolithic material, with a perfect surface created from a chaotic pile of scraps? In this video, we'll show you every step, from metal separators that pull nails from the waste, to giant presses with temperatures over 400 degrees. And if you watch until the end, you'll discover a secret that will change your perception of furniture. It all begins at a huge raw material yard, where the foundation for the future particle board arrives in a continuous stream. This is a place where the idea of rational resource use is brought to life on an impressive scale. Contrary to popular belief, high-quality commercial timber is almost never used for particle board production. Instead, the production philosophy is to give a second life to wood waste, turning what was previously considered a byproduct into a valuable material. Piles of raw material, reaching tens of feet high, are brought here. The base is technological chips, obtained from low-quality wood that is not suitable for lumber production. A huge share consists of waste from sawmills, slab wood, which is the side parts of a log with a rounded surface, board offcuts, and thin strips that remain after log cutting. Woodworking waste, such as shavings and sawdust, generated at furniture and carpentry factories during planing and milling, is also actively used. A separate and important direction is secondary wood. Old wooden pallets, crates, packaging, and even used furniture, after a thorough cleaning process, get a chance for a new life as part of a particle board. Every batch of incoming raw material undergoes strict incoming inspection, as purity is the key to quality. The first stage of cleaning is the removal of metal inclusions. Powerful electromagnetic separators, capable of pulling a steel bolt from a distance of several inches, sift through the stream of raw material, removing nails, staples, and any other metal fragments that could catastrophically damage the expensive shredding equipment. Next, the raw material passes through screening systems to remove mineral impurities, sand, stones, and other debris that act as an abrasive and quickly dull the cutting tools. If whole logs are used in production, for example, 20 feet long, they must pass through a debarking machine. In a huge rotating drum, or with the help of special cutters, the bark is removed from them. This step is critically important, as bark has a different structure, contains a lot of dirt, and significantly worsens the quality of wood chip bonding, as well as negatively affecting the appearance and strength of the final product. The prepared and cleaned wood begins its journey on a conveyor belt hundreds of feet long, which relentlessly carries it to the first stage of mechanical transformation. It disappears into the steel maw of a giant chipper, an industrial monster the size of a small room, capable of swallowing pieces of wood several feet thick. Inside this machine, with a deafening roar that makes the workshop floor tremble, a massive disc equipped with razor-sharp knives rotates. Rotating at a speed of thousands of revolutions per minute, these knives cut into the wood with incredible ease, turning whole pieces into a stream of uniform chips a few inches in size. But this material, despite its uniformity, is only a semi-finished product. The resulting chips are too large, coarse, and non-uniform in shape to create a quality particle board. Their cubic structure would not allow for the creation of a dense and monolithic structure. Therefore, the next step is a finer and more delicate secondary grinding, which takes place in specialized flakers or mills. It is here, in the hum of high-precision equipment, that the very particle that gave the final product its name is born. At this stage, the geometry of the chip becomes crucial, as it is designed with engineering precision. For the outer, face layers of the particle board, which will be responsible for its appearance and smoothness, very fine, thin, and flat flakes are needed. They are produced in knife ring flakers, which literally shave thin flakes from the chips, resembling flakes only a few hundredths of an inch thick. These flakes, having a large surface area, perfectly bond with the resin and form a flawlessly smooth surface, ready for further processing. In contrast, for the inner central layer of the board, which is its structural backbone, larger and thicker flakes are used. They create a strong internal frame that gives the particle board its final rigidity, bending strength, and the ability to securely hold fasteners, such as screws and bolts. The resulting chip mass has varying moisture content, which is unacceptable for quality bonding. Therefore, all the chips are sent to one of the most important stages, drying. Usually, huge drum dryers are used for this. The chips are continuously fed into a rotating drum, where they are blown with hot air or flue gases. The process is strictly controlled by automation. The final moisture content of the chips must be in a very narrow range, from 2 to 6%. If the chips are over-dried, they will not be properly saturated with glue. If they remain too moist, during hot pressing, the excess water vapor can rupture the board from the inside, forming defects. The dried chips are not uniform in size. To create the correct 3-layer structure of the board, they must be sorted. The chip mass passes through a system of mechanical screens or air separators. Heavier and larger chips, intended for the inner layer, settle first. The lighter and finer fraction for the outer layers flies further. This process allows for obtaining 2 or more streams of chips of different geometries, which will be used to form the sandwich of the future board. Now it's time for the key component that will turn the loose mass of chips into a monolithic board, the binder. Most often, these are synthetic resins, mainly urea formaldehyde or melamine urea formaldehyde. The sorted chips enter special continuous mixers. Inside them, the resin is sprayed through nozzles, creating a glue mist that evenly envelops each particle of wood. The dosage of the resin is critically important and is usually from 6% to 10% of the mass of dry chips. Along with the resin, other components may be added. The resinated chips, now sticky and ready for bonding, are finally ready to become a board. They are transported to a massive forming machine, where a continuous chip mat is born from the scattered particles. It is here that the engineering magic of creating a 3-layer structure takes place. The forming machine is a complex system that sequentially and with high precision sprinkles chips onto a moving conveyor belt. First, it creates a perfectly even bottom layer, using the smallest fraction of chips. Immediately after this, a much thicker middle layer, consisting of large and strong chips, is laid on this base. Finally, the entire mat is covered with another layer of the fine fraction, creating a mirror image of the bottom layer. This carefully designed structure, resembling a sandwich, provides the unique properties of the future board. Its smooth and dense outer layers are ideal for further sanding and laminating, while the strong inner layer gives the board the necessary rigidity and the ability to securely hold fasteners. The formed but still loose mat passes through a pre-press, where it is significantly compacted. This pre-pressing removes excess air from it and gives it a shape convenient for loading into the main press. This is the culmination of the entire technological process. The pre-pressed and cut into fragments of a given length mat is fed into a hot press. This can be either a giant multi-opening press of periodic action, which simultaneously compresses a whole stack of boards, or a modern continuous press of the belt type. Inside the press, the chip mass is simultaneously affected by 2 powerful factors. Huge pressure, reaching tens of kilograms per square centimeter, compresses the chips, leaving no voids between the particles. At the same time, the press platens, heated to a temperature of 400 degrees Fahrenheit, transfer their heat to the mat. This high temperature activates the resin, launching an irreversible polymerization process. The liquid glue instantly turns into an extremely hard and strong polymer, which permanently glues millions of wood particles together. The time spent in the press depends on the thickness of the board and usually lasts only a few minutes. During this short period, the loose mat turns into a hot, hard, and absolutely monolithic particle board. The hot boards after the press cannot be stacked immediately. They need to be cooled gradually to relieve internal thermal stresses and avoid further deformation or warping. For this, they are placed in special star or fan coolers, where they are blown with air for several hours until they are completely cooled and their structure is stabilized. The next step is calibration and sanding, which gives the board a marketable appearance. The boards pass through sanding machines with several heads, where wide abrasive belts remove a thin surface layer, bringing the board to a precise specified thickness and creating a perfectly smooth surface. At the final stage, the large technological boards are cut into standard commercial formats, and their edges are trimmed. The finished product undergoes strict quality control, where its density, bending strength, moisture content, surface quality, and dimensional accuracy are checked. Only quality boards are marked and sent to the warehouse. From there, their path lies to furniture factories, where they will be transformed into familiar household items, silently demonstrating the amazing journey from unnecessary chips to a functional and indispensable foundation of our comfort.